I'm William Swartworth, and I'll be talking about joint work with David Woodruff on approximating eigenvalues of matrices via sketching. In the modern big data setting, matrices can have extremely large dimension. For example, we could be interested in a matrix, which is the empirical covariance matrix of millions or tens of millions of data points. And in that situation, we could have matrices that have dimensions in millions or tens of millions. So we're interested very broadly in developing efficient algorithms for basic linear algebra primitives. So one such primitive is computing the spectrum. So this is a very natural and useful primitive in certain situations. And we'd like to know how efficiently can we compute the spectrum. So a very natural way to compute the spectrum is to run power method. However, this requires that we can compute matrix vector products adaptively. So we compute A times V, and then we'd use the result of that computation to compute A times V, and so on. However, in some situations, we might be interested in compressing our matrix. So this comes up, for example, in streaming settings, where we get streaming updates to our matrix, and we'd like to apply some sketch to our streaming updates to keep track of a compressed version of the matrix. So our question is, how well can we do via sketching? So we'd like to form a sketch of our matrix, and from the sketch, recover the spectrum as well as possible. So for our problem, we're assuming that A is a symmetric D by D matrix. And importantly, we're not going to assume that A is PSD. So A is allowed to have negative eigenvalues. We'd like to construct a linear sketch of A, and then recover the eigenvalues of A from the sketch. So A is some very large matrix, potentially with huge dimension, and we'd like to form a smaller sketched matrix that has much smaller dimension. So our goal here is going to be to recover the eigenvalues of A to within epsilon times Frobenius norm of A additive error. So maybe a multiplicative guarantee would be more natural. We'd like to recover all the eigenvalues perhaps up to 1% error. But unfortunately, there's been prior work that rules this out for sketches. For sketches, we can't hope to get a multiplicative guarantee, at least without dimension dependence in the sketch. So here our goal is going to be to get a sketch where the sketching dimension only depends on our error epsilon. Okay, so our question is, how small can such a sketch be? We'd like to recover all of the eigenvalues of A, including the sign, to within epsilon times Frobenius norm of A additive error. I'd like to mention a couple pieces of prior work. The first is a result by Andoni and Nguyen on approximating the singular values of a matrix via sketching. So what they show is that given a matrix A, they sketch it on both sides by a different Gaussian matrix. And then they show that the singular values of the sketched matrix are good approximations to the singular values of the original matrix. So their sketching guarantee has both a multiplicative component, that's the epsilon times the singular value of A term, and an additive component that depends on the Frobenius tail of A. So A sub minus K is A with the top K eigenvalues removed. So they obtain this approximation guarantee on the top K eigenvalues of the matrix for a given sketching dimension. So while their sketch is relevant in our setting, it loses sign information immediately because G H transpose and G minus A H transpose both have the same distribution just because Gaussian matrices are symmetric, meaning the distribution of G and the distribution of minus G are the same. In the PSD case, however, their guarantee applies, and by plugging in appropriate epsilon and k, we can obtain our epsilon times Frobenius norm of A additive error if we sketch to 1 over epsilon cubed on each side. Our goal is going to be to beat 1 over epsilon cubed and to also preserve sign information of eigenvalues. So I'd also like to briefly mention work by Cameron Musco and others on approximating eigenvalues of a matrix by sampling. So this is for matrices in the bounded entry model. They show how to subsample the matrix and approximate the eigenvalues of the original matrix by sampling the principal minor. So they obtain approximation guarantees that are similar to the additive guarantee that we're aiming for here. Our approach is to take a bilinear sketch of the form GAG transpose, where the entries of G are independent Gaussians. So we'll sketch down to dimension k on both sides from a potentially much larger matrix of dimension d by d. This sketch at least has a chance of preserving sign information, because, for example, if A is positive semi-definite, then GAG transpose is also going to be positive semi-definite. We'll normalize our sketching matrix so that GAG transpose has trace, which is a trace estimator for A. So for our sketched matrix, the sketched eigenvalues center around 1 over k times trace of A, since there's k eigenvalues and they sum up to roughly trace of A. On the other hand, the original matrix A had eigenvalues that summed up to trace of A, but there were d of them, so they centered around 1 over d times trace of A. So this means that the eigenvalues of our sketched matrix potentially center around a much larger value than the eigenvalues of the original matrix. So we need a way of correcting for this, and we correct this by subtracting off a bias term, which is the difference between where the eigenvalues of A center and where the eigenvalues of the sketch center. So we'll take our sketch matrix GAG transpose and then subtract off 1 over k times trace of A minus 1 over d times trace of A, which is the difference between the average of the sketched eigenvalues and the average of the original eigenvalues. The 1 over d times trace of A term is very small relative to 1 over k times trace of A for the situations that we're interested in. So for our algorithm, we can omit the 1 over d trace of A term without changing the asymptotics. It just makes the algorithm look a little simpler. Our algorithm is to first draw a sketching matrix G, which is going to be k by d. So we'll sketch down to small dimension k. G is going to have IID Gaussian entries with variance 1 over k. And then we form the sketch GAG transpose as before, so we'll call the sketched matrix S. And then what we'll do is we'll output the eigenvalues of S, but shifted by trace of A over k, right, to correct for this increase in eigenvalues that we get when we sketch. So the eigenvalues of this shifted sketch are going to be our estimates for the top k eigenvalues of A. And then for the remaining eigenvalues of A, we'll simply estimate those to be 0. So this gives a very simple algorithm. It's easy to implement. And in this setting, it gives optimal additive guarantees. So what we'll show is that when k is at least 1 over epsilon squared, this algorithm estimates all the eigenvalues of A to within epsilon times Frobenius norm of A additive error. The first step of the analysis is understanding the contributions of the small eigenvalues. So we'll just assume throughout that A is normalized to have Frobenius norm 1, and so we're interested in approximating the eigenvalues of A to within epsilon additive error. So we start by splitting A into the large eigenvalues and the small eigenvalues. So A sub L is A, but with the small eigenvalues zeroed out. So we project it onto the eigenspaces, or the span of the largest eigenvectors of A. And A sub S is just A with all the large eigenvalues zeroed out. So the large eigenvalues are the eigenvalues that we're interested in approximating, and the small eigenvalues are the eigenvalues that we're okay just rounding to 0. So A sub L has at most 1 over epsilon squared non-zero eigenvalues. That's just because if it had more than 1 over epsilon squared non-zero eigenvalues that were larger than epsilon, then that would mean that the Frobenius norm of A would be larger than 1. Since G is a Gaussian matrix, the eigenvalues of G times AS times G transpose concentrate well around 1 over K times trace of AS. So we know that the trace of GAS, G transpose, is going to be a trace estimator for AS. So we therefore expect that the eigenvalues should concentrate around 1 over K times its trace. However, here the reason that we get good concentration is because we're assuming that the eigenvalues are small. So assuming that the eigenvalues of A sub S are small, which they are, they're smaller than epsilon, we get good additive concentration within epsilon around 1 over K times trace of AS. So that's the contribution of the small eigenvalues. But on the other hand, the large eigenvalues don't contribute much mass here. If we take 1 over K times the trace of the large eigenvalues, well, the trace of the large eigenvalues is bounded by 1 over epsilon times the Frobenius norm of the large eigenvalues, just because A sub L has at most 1 over epsilon squared non-zero eigenvalues. So since K is going to be at least 1 over epsilon squared, 1 over K times the trace of AL is bounded by epsilon. So when we sketch the large eigenvalues, they don't contribute much mass to the trace. And so when we shift GAG transpose by 1 over K times the trace of A, this sort of corrects for the contribution of the small terms. So the idea is that we took A, we decomposed it into the large eigenvalues and the small eigenvalues. We then imagine sketching A, that split it up into the sketch of the large eigenvalues plus the sketch of the small eigenvalues. And we didn't care about the small eigenvalues, so we got rid of them, or we got rid of the contribution from the small eigenvalues by subtracting off this 1 over K times trace of A term. Understanding the contributions of the small eigenvalues was fairly straightforward, and we could simply subtract off their contribution. The remaining part of the argument is to understand how the large eigenvalues behave when sketched. So A sub L, which was our large eigenvalues, we said the matrix A sub L had at most 1 over epsilon squared non-zero eigenvalues, because A had at most 1 over epsilon squared eigenvalues that were at least epsilon. So since we've understood the contributions of the small eigenvalues, we just need that the eigenvalues of G, AL, G transpose are good additive approximations to the eigenvalues of A sub L. So there's two steps here. We need to first get an upper bound on the eigenvalue, on this sketch of the large eigenvalues, and then we need to get a lower bound on the sketch of the large eigenvalues. So we'll look at both of those steps in turn. The key to getting upper bounds on the sketched eigenvalues is the following lemma that we prove. So D is an n by n matrix that we assume is PSD. We assume that the Frobenius norm of D is bounded by 1. And then G is just a normalized Gaussian matrix. So the quantity on the left-hand side is a Gaussian matrix, but with non-identity covariance. And so we're interested in bounding the singular values of that matrix. So the bound that we get is the largest eigenvalue of D plus a 1 over root K term, where K is the sketching dimension. So we can think of this as a bound on the top singular value of a Gaussian matrix, but with non-identity covariance. In the situation where D just has flat spectrum, then this reduces to the standard bound on the top singular value of a Gaussian. The previous result let us get an upper bound on the top eigenvalue of the sketch. However, we'd like to get an upper bound on all the eigenvalues of the sketch. So we'll use the previous result, but apply it to deflations of the matrix that we're sketching. So let D be an n by n matrix. It doesn't have to be PSD, and we have the same bound on the Frobenius norm. It's bounded by 1. We'll assume that D has at least L positive eigenvalues. And then the claim is that the nth largest eigenvalue of D's sketch is the nth largest eigenvalue of D, or is at most the nth largest eigenvalue of D with epsilon error. And that's going to hold as long as k is sufficiently large. So k will be at least as large as the dimension of D, and also needs to be at least 1 over epsilon squared. So as epsilon gets smaller, we need to have a larger sketching dimension. So this follows as a fairly simple corollary of the previous result. So first of all, negative eigenvalues only help, so we might as well assume that D is PSD. And then we can just apply the previous concentration bound, but to deflations of D. So deflation of D is just D with its top eigenvalues removed. So we can bound the nth largest eigenvalue of GDG transpose by the top eigenvalue of the same sketch, but applied to a deflation of D. So D with its top L minus 1 eigenvalues removed. Right. So with this bound, we can then apply the previous result, which gave us a bound on the top eigenvalue of a sketched matrix, and this proves the lemma. The next step is to get a lower bound on the sketched eigenvalues. So the first step to do that is to handle the PSD case. So we'll say that M is an n by n PSD matrix, as opposed to D, which wasn't PSD. Again, the Frobenius norm of M we're assuming is bounded by 1, and G is the same sketching matrix from before. So then, as long as our sketching dimension is first of all at least as large as the dimension of M, so that we don't lose any of the eigenvalues of M, and at least 1 over epsilon squared, where epsilon's our error parameter, then the nth largest eigenvalue of the sketched matrix is at least the nth largest eigenvalue of M up to our error parameter epsilon. So I should mention here that M is n by n. In our final result, we're going to apply this lemma where M is the matrix of large eigenvalues. So n is going to be eventually 1 over epsilon squared. So we'll only ever require a sketching dimension of 1 over epsilon squared transpose, which is the nth largest eigenvalue of GMG transpose. We first write that it's equal to lambda L of the matrix on the right. So to see that, we just use the fact that M is PSD, so it has a square root. You can replace M on the left with M to the 1/2 times M to the 1/2. And then we can swap the two terms around using the fact that switching a matrix with its transpose preserves the spectrum. At least that's true as long as the matrix on the left has large enough dimension to actually have an nth eigenvalue. So this is why we assumed that the sketching dimension of G was at least n. That ensures that G has dimension at least L, and so the expression on the left-hand side makes sense. So we know that M to the 1/2 is large, at least larger than lambda L, on some L-dimensional subspace SL. So here the subspace SL is just the span of the top L eigenvectors of M. So for any x in the span of the top L eigenvectors of M, the quadratic form associated to M is going to be at least the nth largest eigenvalue, which is what this inequality is saying. What we'd like, however, is to argue that G times M to the 1/2 is large over an L-dimensional subspace. So we can make that happen as long as G approximately preserves the norms of all the vectors in SL. In fact, what we'd like is that G approximately preserves the norms of all the vectors in m to the 1/2 times SL. But SL was just the span of the top eigenvectors of m, so m to the 1/2 times SL is just SL. So we'd like that G approximately preserves the norms of everything in SL. And the distortion factor that we need is 1 plus or minus epsilon over lambda L of m. Right. In that case, then we can say that the norm of G times m to the 1/2 x squared is at least lambda L of m minus epsilon on SL. Right. So as long as G approximately preserves the norms of the vectors in SL, then G times m to the 1/2 is going to give a good additive approximation, or it's going to be at least lambda L of m to within additive error epsilon on SL. So how do we ensure that G is a 1 plus or minus epsilon over lambda L distortion subspace embedding? Well, G is just a Gaussian, and we can use standard bounds for subspace embeddings. The sketching dimension needs to be 1 over the distortion factor squared, so that gives lambda L of m squared over epsilon squared. And this was an L-dimensional subspace, so we pick up an extra factor of L. So we need a sketching dimension of at least lambda L of m squared over epsilon squared times L. But here we can bound this because we made an assumption on the Frobenius norm of m. Since m had Frobenius norm at most 1, the Lth largest eigenvalue of m is at most 1 over root L. So lambda L of m squared is at most 1 over L. And therefore, taking k to be 1 over epsilon squared suffices. So for general m, we decompose it into its positive and negative parts. So we write it as m plus minus m minus, where both terms are PST. And then we have to be worried that the eigenvalues of the negative part of the sketch could interfere with the eigenvalues from the positive part of the sketch. So to avoid this, the idea is to first prune off the large magnitude eigenvalues of G m minus G transpose. Then we show that we can find an L-dimensional subspace that's orthogonal to the large eigenvalues in the negative sketch, and on which the positive sketch is uniformly large. So with those two pieces, then Courant-Fisher implies that the Lth largest eigenvalue of the full sketch is large. What we did is we first decomposed A into its large and small eigenvalues. We showed that when we sketched the small eigenvalues, we ended up with a matrix whose eigenvalues are all at most epsilon. So the sketched small eigenvalues don't cause too much perturbation. When we sketch the large eigenvalues, we get a matrix whose eigenvalues are good approximations to those of the large eigenvalues of A. Therefore, combining these two results, we get that the eigenvalues of GAG transpose are good additive approximations to those of A. We showed that we can recover all eigenvalues of A to within epsilon times Frobenius additive error by taking a 1 over epsilon squared by 1 over epsilon squared bilinear sketch. And we were able to recover all eigenvalues of A, including sign, even when A is not PST. So we know, in fact, that 1 over epsilon to the 4th sketching dimension is optimal, even if we're not restricting ourselves to bilinear sketches, and even if we're only interested in approximating a single extreme eigenvalue. So our sketching dimension here is optimal. And in fact, it's even optimal if we allow adaptive matrix vector products. So if you're allowed to make matrix vector queries to A, where future queries can depend on the results of prior queries, then we know that 1 over epsilon squared measurements are necessary. And in fact, 1 over epsilon squared measurements is exactly enough to implement our sketch. with matrix vector products. So in fact, adaptivity doesn't help in this situation. So this gives two sort of measurements under which our sketch gives an optimal guarantee. Finally, I'll close with two open problems. The first is that sketching by a Gaussian on both sides is fairly slow. But there's faster sketches known throughout the literature. So for example, can we achieve the same sketching guarantee that we get here, this epsilon Frobenius guarantee, by a sketch that runs in input sparsity time? So meaning linear in the number of non-zero entries in A. Our analysis relied on Gaussianity, mostly to control the small eigenvalues. And we don't know how to get a similar guarantee for sparse sketches, for example. Another question is how many adaptive linear measurements are needed to achieve the same guarantee? We partially answered this question by giving a lower bound for matrix vector products. But for general linear measurements, if they're allowed to be taken adaptively, we suspect that 1 over epsilon to the fourth is still optimal, although we don't know how to prove it.